Okay, perfect. Laura?
Okay, so good afternoon, everyone. I'm glad to introduce you to Paul Jarvis. He's our guest from GNS in New Zealand. I think it's the last week we can call it GNS because it will change the name soon. So let's still use the old name. Paul graduated in 2012 in Cambridge in the UK, where he's originally from, in physics. And then he earned his PhD in Bristol, which is like the big place for volcanology, in 2016. Then he took a break from volcanoes. Mistakes happen. So
I needed a job.
he did his first postdoc on sand dunes but he started running some analog experiments, and he's still doing this. So this fun part, still doing it. And he did this in Cambridge, and then he moved to Geneva for another postdoc, now again in volcanology, on analog experiments, on ash sedimentation. And then he has got a permanent position in GNS since 2021. He's a researcher, and he does research and monitoring in physical volcanology. That's what we ended up. So he's here in Bologna. He's been here for 2.5 weeks now. He's staying until the end of this week. And I take this as opportunity to advertise the fact that he's here thanks to a transnational access funding from GeoInquire EU project. And at present, there is another call for to ask and apply for transnational access for this project. So any of you that are interested in going somewhere else, you can go on the GeoInquire webpage and maybe take the opportunity, as Paul has done, to get funding to travel to some other countries for a small project. Flores is yours.
Okay. Thank you very much, Laura, for the introduction. And also thank you to you and Beatrice for welcoming me to Bologna for the last 2.5 weeks and working with me on this project. I'm just going to share the screen. Can people online confirm they can see the slides? All good? Hang on. Let me do this again.
You can see the slide. Yeah, we can read.
Okay. My laptop is slowing down.
Okay, so you can switch to the PowerPoint then. If your laptop responds.
There we go.
Okay.
Yes, all good. Okay, perfect. Okay. So yeah, as Laura said, I'm going to be talking about the 2022 eruption of Hunga volcano in Tonga. Before I get into it, I really want to emphasize that the work I'm going to show today is the result of a quite wide collaboration. I've only really been involved in just a part of it. And as I go through the different topics of this talk, I will try to highlight where the relevant individuals who have led to these different pieces of work have done so. So what I'm going to go through briefly is I'm going to introduce Hunga volcano and the 2022 eruption and provide a very brief summary of some of the truly remarkable features and phenomena which occurred during the eruption. And then I'm going to go into a little bit more detail about the dynamics of the volcanic plume and the umbrella cloud, and describe how we studied that through a combination of satellite imagery and also data on the volcanic lightning which occurred inside the cloud. Then I'm going to change track slightly and talk about the atmospheric disturbances which propagated through the atmosphere from the eruption, and then I'm going to sort of tie that back into the umbrella cloud and plume dynamics. Finally, I'll present a little bit of an eruption chronology that we've managed to extract from these two pieces of analysis, and then provide some perspectives on future work along with the summary. So, introduction to Hunga and the 2022 eruption. So Hunga volcano is a caldera volcano on the Tonga Kermadec arc. So this is Australia here, this is New Zealand, and Tonga and Hunga volcano is where the red dot is. The caldera itself, this is a bathymetry map from 2018, so prior to the 2022 eruption. Most of the caldera is submerged, but back when the survey was done, there was, or prior to 2014, there were two parts of the caldera above the ocean surface. You had this island here, which is called Hunga Hapai, and this island here, which is called Hunga Tonga. Certain eruptions, so phreatomagmatic events in 2009 and 2014, 2015, occurred from a couple of different vents along the northern side of the caldera, with mostly activity sort of centered between the two islands. And in the 2014-2015 activity, this cone here formed. However, other colleagues in New Zealand have done field work on these two islands. This was prior to 2022, and also on the other Tongan islands. And they've shown that repeated caldera-forming eruptions have occurred in the geological past. Most recently, prior to 2022, sometime between 1040 and 1180. Then, in December 2021, a new eruptive phase of Surtsey-style activity started. So this is some footage which was captured by our colleagues from Tonga Geological Services. So they are the monitoring agency in Tonga. This was captured near the start of that sequence. You can sort of see very typical Surtsey-style behavior, along with some more white plumes, presumably with a lot of water vapor, which is forming from interaction with the magma. And this behavior was very similar initially to what happened in the previous episodes in 2009 and 2014, 2015. This sort of continued waxing and waning until the 13th of January, 2022, when a much larger eruption occurred with a plume up to 18 kilometers altitude. And that actually, Tonga Geological Services happened to be out on a boat that day and managed to capture some really good footage of that particular event. That eruption itself lasted for about 14 hours. And after it was done, this high resolution satellite image was captured of the two islands. And you can see that where this cone, which I pointed out in this bathymetry was there, that was destroyed in the 30th of January eruption. So this satellite image happened to be taken about 2 hours prior to the cataclysmic eruption on the 15th of January. Which I'll now talk about a little bit. So, some of the remarkable features of this eruption. Probably the first remarkable feature is that the height of the volcanic plume reached a maximum of 58 kilometers. And so this plot here, this comes from a study by Proud et al. On the top right plot here, you have height on the y-axis and time on the x-axis. And they compared a few different measurements to methods of extracting plume height from satellite imagery, but the points are probably what's most reliable. You can see that there was a very rapid rise in plume height up to, they measured, I think, 55 kilometers, other authors got 58. But then what's quite important is that there was a very dramatic oscillation in height, back down to 40 kilometers and then back up again. So that's the maximum height of the plume that they measured. The other remarkable thing, which you can take away very quickly, is that there was very rapid growth of the umbrella cloud. So that's plotted in this plot on the bottom right. We have the radius of the umbrella cloud as a function of time. And you can see that within the first hour of the eruption, the umbrella cloud grew to a radius of about 200 kilometers. Another remarkable feature was that various atmospheric perturbations were generated and propagated across the globe. This included various acoustic waves. So sounds from this eruption were heard as far away as in New Zealand and also in Alaska. And this is a result of this map on the right-hand side here is a result of a study by a colleague of mine at GNS, Rachel Lawson. And this is, she collected basically observations from the public of the sounds which were heard. So all the red dots in this map are people who reported hearing sounds from the eruption. And it's quite interesting to think about what they heard. Some people in New Zealand, their initial thoughts was maybe it was one of our volcanoes in New Zealand. Multiple people said they went and checked if it was White Island erupting or Ruapehu erupting. In fact, the person who was duty volcanologist at GNS on the day got a phone call from a policeman asking if Ruapehu was erupting. Some people said that the sound was loud enough to give them a fright. So it's quite spectacular that this far away from Tonga, people heard sounds this loud. Various gravity waves were also generated by the eruption. Now, gravity waves are perturbations to the atmospheric stratification, and they're more commonly observed, or are commonly observed, due to topographic interaction. So in this image in the bottom left, if you have air currents rising up over topography, you'll get oscillations of the altitudes of those currents as you move downwind from the topography. And this study here, the authors, on the right-hand side, you can see that they've superimposed, stitched satellite imagery above the globe. And looking at the brightness temperature of the satellite imagery, you can see the gravity waves propagated out from the volcano pretty much over the whole globe. There was also a long period LAM wave. So the LAM wave is a longitudinal wave which transverses the full depth of the atmosphere. And we were able to track this in New Zealand. So on this map on the right-hand side, Hunga is the red dot again. And each of the yellow dots is an atmospheric pressure measurement station, which is operated by our meteorological service. And in the plot here on the bottom left, you can see measurements of the air pressure measured as a function of time. You can see that for different stations moving from north at the top to south at the bottom, you can see that this wave with a very characteristic N shape propagated across the country from north to south. And that's this LAM wave, which was generated, low frequency LAM wave, which was generated from the eruption. And we could backtrack the propagation of that, which we did here, to estimate an origin time of 4:15 UTC on the 15th of January. That time coincides with the primary seismo-acoustic event detected in the eruption. What was quite spectacular about the LAM wave is that it was observed to generate a meteo tsunami. So this image on the bottom left is a simulation by Guzman et al. Of the front of the LAM wave propagating away from Hunga. And on the right, they simulated the interaction of that with the ocean surface, and they showed that it was able to generate a tsunami. This was quite a small amplitude tsunami. It didn't have too much in the way of far field impacts, but this tsunami was actually observed to, because it's generated by an air wave, it could jump across land masses, and it was even observed in the Caribbean. There was also an awful lot of volcanic lightning generated in the eruption. So in this animation here, each red dot is a located strike of lightning. So more than 300,000 lightning strikes were recorded within the 2 hours after the eruption. Volcanic lightning is a fairly well-known phenomenon in explosive eruptions. There's a compilation of images here from other events. But this particular eruption, these were the highest lightning rates ever documented on Earth, whether in a thunderstorm or in a volcanic eruption. And I'm going to talk a little bit more about the lightning later on in this talk. One of the biggest impacts of the eruption is that underwater telecommunications cables were destroyed. So this map here, this is Hunga volcano, represented by the yellow marker, and then the dotted red lines are telecommunications cables, which go the international cable, which runs along the bottom, goes to Tonga, I think from Fiji, and the domestic cable, which runs along the vertically on the right of the image, goes between Tongan islands. Both of those were severed during the eruption. And based on the timings at which those cables were severed, which can be known exactly because people know the time at which the signals travel along them ended, people were able to make some constraints on the speed at which mass pyroclastic density currents propagated away from the volcano and ultimately destroyed these currents. And the speeds of these flows exceeded 100 kilometers per hour, which I think these are supposed to be record speeds for underwater mass flows. What's also quite interesting is that these flow trajectories were heavily controlled by the topography. In fact, one part of the international cable was actually found, it had moved closer to the volcano rather than away, and that's because where the flows had been funneled by topography, the flow was effectively funneled back towards the volcano. And you can sort of see that demarked with one of these gray arrows here. Finally, pre-eruption, the caldera, its deepest point in the bathymetry, that's the bathymetry medium on the left, that was about 200 meters deep. Post-eruption, the bottom of the caldera was now 800 meters deep. Despite that dramatic change, the actual edifice of the caldera walls remained remarkably intact. So beneath that, we have a pair of cross sections across the caldera floor. The light gray line shows the pre-eruption bathymetry. The dark line shows the post-eruption bathymetry. So you see that the walls for caldera are remarkably resilient, but an awful lot of material, in fact, estimated to be about 6.3 kilometers cubed, was removed. And people have done bathymetry on the mass flow deposits, suggest that most of the material ended up in those mass flows rather than in tephra. So this really was an unprecedented eruption in the period of modern observations. And it really leads to a very large number of questions, which we don't really have answers to. Why was the eruption so energetic? How physically can you get a plume to reach so high? How did interaction with seawater, with the magma, affect the dynamics of the plume? What are the climatic impacts of the eruption? Why was there so much intensity in the volcanic lightning? How were the atmospheric disturbances generated to the extent that you could hear the eruption so far away? So those are really big questions. And there's already quite a substantial and growing body of literature looking at these. Today, I'm mostly going to focus on the plume and umbrella cloud and really look at what the relationship, firstly, between the volcanic lightning and the eruption dynamics was. Secondly, the generating mechanisms of the atmospheric disturbances. And finally, a little bit of eruption chronology, which we've managed to piece together from last answer those two questions. So the umbrella cloud. Very quick 101 on volcanic eruption plumes and umbrella clouds. When a volcano erupts and this hot mixture of rock and gas comes out of the vent, initially the density of that material is greater than the density of the air immediately surrounding it. But as that comes up as a jet, it rapidly entrains atmospheric air around it. That air gets heated up. It rapidly expands. And so the bulk density of that mixture very rapidly decreases. And then at this height, represented by the lowest dotted line, the density of the erupted mixture has become less than the density of the surrounding atmosphere. That means it is now buoyant, and so it can rise up by buoyancy in what we call the convective zone. However, as it's going up, the density of the surrounding atmosphere is also decreasing. And so at some point, the two densities equal again. That's this top dotted line, which we call the level of neutral buoyancy. At that point, there isn't a density difference between the plume and the atmosphere. And so you have a bit of overshooting due to momentum, and then you get spreading of an umbrella cloud laterally. Now, if you apply a force balance between the driving buoyancy force in the spreading umbrella cloud and resisting inertial forces, so that's the force you need to really displace the air, which you're moving out of the way, you can estimate a theoretical expression for the rate of spreading where the radius of the cloud is proportional to time to the power, to the 2/3 power. And using that relationship, if you can fit observations of cloud radius as a function of time, for example, if you get these observations of satellite imagery, you can make inferences about what the volume flux into that umbrella cloud is. So this is something we did for the umbrella cloud from Hunga. And the data is what you can see down here in the bottom right. So on the y-axis, you have the umbrella radius. On the x-axis, you have time. And the red points are the measurements. And then in the inset, you have the same, but on a log-log scale. And what you can see is that the spreading over the whole time period is clearly not described by a single power law. The earlier spreading might be well fitted with a power law of time to the 2/3, approximately, but our confidence in that is very limited because we only get one satellite image every 10 minutes, and the cloud is evolving on a timescale much quicker. But the late spreading is definitely a lot slower than what is predicted by that 2/3 law. Now, you can come up with some more complicated models of cloud spread than just this scaling expression of time to the 2/3. And you can derive these, so I'm not going to derive them now, but you can derive these if you allow the horizontal velocity, u, and the current thickness, h, to vary with the radius outwards. So that's the velocity inside the cloud. And if you do that, you can solve what are called the shallow water equations. They're really ugly, I'm not going to show them. And that actually allows you to enable modeling a wide suite of scenarios. So for example, you can, once you've got those equations, you can make approximations as to whether the spreading is being resisted by inertial forces, or what we call turbulent drag, which is effectively friction on the top and bottom surfaces of the cloud? Or do you have what's an instantaneous injection of mass followed by spreading afterwards, or do you have a continuous injection of mass? And if you make approximations, you can find alternative power laws in each of these 4 limiting cases. So comparing the outcomes of these limiting cases of the shallow water models with the observations, what we can tell is that potentially the inertial drag regime, so where your umbrella cloud spreading is dominantly being resisted by the force needed to displace the atmosphere, that may be appropriate. And it may be that about 7 minutes past 5 UTC, we have a transition from this continuous regime. So until then, the umbrella cloud is still being fed from below to what we call the instantaneous regime. So maybe later than that, you're no longer getting more material into the umbrella cloud. It's just continuing to spread out by the buoyancy it has left over. There are massive caveats in these conclusions. As I said, we only retrieve satellite imagery every 10 minutes, which means the uncertainties on the fitted exponents in our data are quite high. Additionally, these models are only applicable once buoyant spreading actually begins. And a lot of that initial spreading is going to be just due to the outward momentum of your cloud. So you have to sort of, in your data, identify a time zero, which is very hard. And also, during the evolution of the umbrella cloud, it is transitioning between these regimes. And so that limits the duration of time in which a single regime applies, and the time actually taken to transition between regimes can be comparable to the time actually spent in a given regime. And so on the whole, it's actually quite difficult to use satellite observations to determine which of these regimes, if any, a spreading umbrella cloud is in. However, can we try and use volcanic lightning data to reduce the uncertainty? And that seems a bit of an out there idea, but the reason behind it is that actually the temporal resolution of the lightning strike locations is at a sub-second resolution, as recorded in this global lightning dataset by Vaisala. And you can see there's also quite a lot of spatial data in these lightning strike locations. So maybe we can use that to try and tell us something about the spreading of the umbrella cloud and the internal dynamics inside the cloud. So before I get into how we use the lightning to study the Hunga Tonga eruption, I'm just going to briefly introduce the background behind volcanic lightning generation. Why do we get lightning in volcanic clouds? So the first step to generating volcanic lightning is that you have to charge or apply an electrical charge on your particles. And this can really happen. And when we're talking about ash clouds or volcanic clouds, there are two types of particles in the cloud. You have volcanic ash, and that can be charged through either triboelectrification, which is particles collide and can exchange charge, or you can have fractoelectrification, which is when you fragment your particles and they get opposite charge, the fragments get opposite charges. The other important aspect of volcanic clouds is that if the cloud gets high enough, you can start to nucleate ice particles, and that can increase the number of particles in your cloud drastically. And so you have much more potential for this triboelectrification process. And so there have been examples where ice has effectively supercharged volcanic clouds. Anak Krakatau, for example, Bogoslov or Tau volcano. These images are from Tau volcano here. So if your cloud plume gets above 10 kilometers and you know there's going to be a decent amount of water in your plume, like we do in the Hunga case, you're going to get a lot of lightning. Then the second step of volcanic lightning generation is you need to separate those charges. This is less understood than the charging process, but the general understanding at the moment is that larger grains become positively charged and smaller grains become negatively charged. Smaller grains, because they have effectively the force of gravity on them is weaker than on larger grains, they have a stronger coupling to the flow of gas in the cloud. So they're going to follow the cloud or the flow of the gas, whereas larger grains may segregate from that a bit. And so you can get a hydrodynamic segregation of different sized particles, and so you can generate an electrostatic segregation. And then once you separate the charges, you get lightning strikes to re-equilibrate, essentially. And so this comes back to the idea where if the charge separation is driven by hydrodynamic processes, then in theory, the distribution of lightning contains information on the flow properties of the plume of the umbrella cloud. Now, the lightning itself, once generated, emits electromagnetic radiation. And in fact, in New Zealand, and also by colleagues in Japan, we have a set of permanent magnetotelluric stations in New Zealand on the land. Normally, magnetotellurics is used where you use the Earth's electromagnetic field to image the subsurface. But here we actually realized that at the time of the eruption, we got large increases in the magnetic field signal at these stations. And if you look at the polarization of that signal, you can show that it's come from the direction of Hunga volcano. And so I showed you the dissected lightning strike locations before. The radio wave portion of the electromagnetic spectrum released from lightning strikes can be used to actually locate individual strikes. And this is now commonly done to characterize explosive eruptions. So in this plot here, I have a plot of the number of lightning strikes in thousands above the volcano as a function of time. This was the peaks on the left-hand side, that long duration event there. That was the eruption of the 13th of January, where you can see there was still a fair amount of lightning generated. But the eruption itself on the 15th generated an astonishing amount of volcanic lightning. And ultimately, the reason for this is that because essentially we had a subaqueous event, large quantities of seawater were entrained into the plume. In fact, some analysis by Larry Mastin at the USGS suggests that you had 8.2 times 10 to the 5 meters cubed per second of seawater going into that volcanic plume. And so it's likely you had very rapid and extensive ice production at high altitudes leading to perfect conditions for lightning generation. And if we look at the spatial temporal distribution of lightning, so what I have here are each image going from left to right, and then down each row is a satellite image where I've segregated out the cloud in gray at 10-minute intervals. And then I've overlain lightning strikes located in the 1 minute either side of that image. You can see that from we saw in the data that about just after 4 there was a rapid increase in the number of lightning strikes. And as the cloud spreads, the lightning initially covered the same aerial extent as the umbrella clouds. In this third image from the left on the top row, you can see that the cloud is entirely covered by lightning strikes. However, just after that, we see that a radial structure starts to appear in the lightning distribution. So in this top right image of 0437, you can see that you have lightning centered immediately above the volcanic vent in the center of the cloud, and then a gap, and then at the outermost radius of the umbrella cloud, you have a ring or an annulus of lightning coincident with the umbrella front. This annulus ring continued to expand until about 0447. And although it didn't really expand much further, you can see at later times you still have remnants of this radial structure present. There's a bit of a mystery. Another way of viewing the radial distribution of lightning is to, what I've done here is what I'm going to show is a video where each frame of the video is the number of lightning strikes in a minute on the y-axis as a function of radius from the center, represented as a histogram. And what you will see is that the annulus of lightning appears as a prominent peak that propagates outwards until it reached a radius of about 120 kilometers. And then that annulus that peak smeared out. And then you even see a few successive peaks appear after that. And this is just another way of depicting what you see. So you see the annulus peaks propagate outwards as you go down this left-hand column by about 0447 at the bottom. That peak is smearing outwards, but then a new peak starts to appear at about 0512, halfway down the second column, which then gradually moves back towards the center. Another way of visualizing this is in this plot here. So in the top plot here, you have radius on the y-axis, time on the x-axis, and the color tells us the density of lightning strikes at that radius at that time. And so this move the mouse just for people online. This front here is the leading lightning annulus. And then you can see that stops spreading at a radius of about 150 kilometers. But even after that, you get successive pulses moving through the lightning cloud, which I've highlighted with the green arrows. So what's our conceptual model for this? So our conceptual model is that we're in that inertial drag spreading regime, and that the umbrella cloud essentially probably has an enlarged head, and that's predicted by the models of Johnson et al. 2015. And in that head, you probably have coherent vorticity. So it's a bit like an expanding vortex ring. And so because you have this vorticity, that could be increasing the rate of collisions in the head of the umbrella cloud. So more triboelectrification. But also, because you'll have different coupling between big and small particles to those flow structures in the head, you may also have increased particle separation as well, so increased separation of shadow. This is depicted, I drew this diagram here in the left, and other people, so this is from me, Ikihara in Tokyo, she drew a much better diagram in the bottom right. At later times, so after this initial lightning ring has decayed away, we probably have a more laminar umbrella, so less vorticity, less charging and or charge separation, and so we don't see so much radial structure. And then these secondary lightning rings, which propagate through, they're possibly caused by gravity waves excited due to oscillation at the top of the volcanic plate. So that's sort of the story of volcanic lightning. And I'm going to spend a little bit of time now talking about the atmospheric disturbances from the eruption. And this really was two pieces of work, one led by Marianne Clive, who was looking at how people in New Zealand observed the sounds, and another one led by Oliver Lamb, who was looking a bit more about the generation mechanisms of the disturbances. So as I said, we surveyed people across New Zealand to see what they heard about the eruption. In the end, we had 1,930 people report to us about what they heard, and we compared what they reported to instrument observations of the atmospheric waves as they propagated across New Zealand from a combination of seismometers across the country, infrasound sensors, which we have installed on New Zealand's volcanoes, our Met services, air pressure sensor network, and also some publicly owned raspberry shake and boom sensors, which the data from which is publicly available. It was quite important to use all of these different sensors because they're all sensitive to different frequencies. So here's a summary again of what people heard. Most people, well, a lot of people compared it to an explosion. Some people said it was more like thumping or thunder or a door slamming. Some people reported that they could feel the waves almost as if you stood next to like a bass system. And what was quite interesting is there was quite a good correlation between the timing of when people reported hearing the sounds. We have in one of these maps in the top right, the left-hand map, the color shows the median time at which people said they heard the sound, versus when we saw the signals on the instrumented data. And also, there was also a correlation between how people identified how loud the sound was to the amplitude of the signals, the audible signals we measured in the instrumented data. So if we look at the actual instrumented data in terms of the acoustic waves, what we have here is a plot of how the different sensors, so the blue lines are atmospheric pressure sensors, the red lines are seismometers from the GNS GeoNet network, and the black lines are what was measured by the raspberry shake and boom. These at the top of the plot are those in the north of the country, the bottom of those in the south. And we're seeing that you can see the propagation of the signals as they move across. So the low frequency Lamb wave was seen by the atmospheric pressure sensors and our infrasound stations, whereas the audible wave packets were seen by the raspberry shake and boom sensors. So the Lamb wave had a celerity or a speed of 313 meters per second, an origin time of 0415, and that agreed with multiple other studies across the globe. But we also identified these two audible wave packets, which are the two pulses in the black lines. Separately, we looked at the seismic data. So these are from seismometers across the country, again, from north to south. And both the audible wave packets, representations of them are also seen in the seismic data. The first wave packet had the same celerity as the Lamb wave, but lagged behind by about 6 minutes. Whereas the second wave packet had a slower celerity, 270 meters per second, compared to 313, and a much later origin time of 0415. Obviously, when we're estimating these origin times, I should note that we're assuming that the propagation speed remains the same in the near field as where we're measuring it out of the far field. So what about the origin of these audible sounds? So it's hypothesized that these audible sounds are due to basically energy cascading from the low frequency perturbation, low frequency waves to high frequencies as the waves are propagating. So wave packet 1 is, we think, is clearly associated with the Lamb wave. It has the same celerity, although why you have a lag of 6 minutes between the arrival of the Lamb wave and the arrival of the acoustic signal is still to be explained. Wave packet 2 is a bit more mysterious. We don't detect any associated low frequency signal passing over New Zealand at the time we saw the second wave packet. However, there are, in other data sets, low frequency wavefronts with comparable speeds, celerities seen. So Watanabe et al. Used satellite imagery, and they identified a wavefront with a celerity of 270 meters per second. And this is an image from their paper here. Hunga volcano is the triangle. And then it's easiest to see if you look up north from that, you can see that one front, which is the land wave, and a second front behind that, which they call the Vicaris wave. And so this Vicaris wave is an atmospheric resonance, which was theorized back in 1938, but had never previously been observed. Something they note is that, or theoretically, the Vicaris wave has a stronger amplitude at high altitudes rather than at the Earth's surface, and that may explain why we don't see that in our censored data. So you have this low frequency wave, which is a high amplitude at altitude, and then that is generating higher frequency signals which propagate down to the Earth's surface and are heard. Maybe further supporting this is these authors, Oya et al. They measured perturbations to the ionosphere from the eruption, and they see the signal as well. So coming back to the land wave, that had an origin time of 4:15. That's coincident with the most energetic seismo-acoustic event. A tsunami, so not the meteo tsunami, but a local tsunami also originated at that time. And there were also ionospheric disturbances at that time. So that's seemingly related to the largest explosion of the eruption. But this Vicaris wave, which originated, more than 30 minutes later, there's no obvious seismic event which happened at that time. There is a major ionospheric disturbance at that time, and there's also an acoustic detection from global infrasound networks. But also, curiously, the largest local tsunami originated at 0456, which is at a similar time. And we also see, back right at the start of this presentation, I showed you that around that time, there were extremely large oscillations in plume height happening, potentially going from 58 kilometers down to 40 kilometers and back up again. And so we propose that rapid injection and collapse of the plume into the upper atmosphere is exciting this Vicaris wave. And in fact, Larry Mastin, I've mentioned this paper already, he showed that even at altitudes of about 40 kilometers, you possibly have plume ascent velocities of 200 meters per second. And so, these are you're going to have large supersonic speeds, potentially generate this. And then literally a couple of weeks ago, this paper came out by Zhang et al., and they performed a waveform inversion of the land wave data. And they found that actually that also came from an apparent source at an altitude of 18 kilometers. And so that suggests that that source could also be similar to what we infer for the Vicaris wave, which is where you have the supersonic injection of the plume umbrella cloud into the upper atmosphere. So it seems that maybe these low frequency waves are not generated directly from the explosions of events, but actually from the injection at high velocity of plume material and then its subsequent collapse in the upper atmosphere. So based on what we've observed, what can we say about the eruption chronology? We know that the lower level eruption began around 4 o'clock. There was the initial infrasound detections were around 0345, and booms were heard on Nuku'alofa, which is the closest inhabited island, around 4 o'clock. But there was a sudden change in eruption style after that, which we see with the rapid increase in lightning from just after 4:10, a rapid increase in the height of the plume, and the onset of the land wave. There was a very rapid increase in plume height and radius after this. Sorry, lost my train of thought. We see that the plume top is oscillating over about a range of 20 kilometers between 0437 and 530. That coincides with the generation of the Vicaris wave around 0450. And we also know that this largest local tsunami originated just before 5 o'clock as well. And importantly, that seems to be not associated with any seismicity. So we speculate that collapse of that material back onto the sea surface generated that. Throughout this time, multiple gravity waves are being generated in the cloud, as recorded in the spatial distribution of the lightning. Yeah, and so coming back to that point I just made about the collapse of material onto the sea surface, what's interesting is that the international cable only broke quite late on in the eruption at 5:44. And so that would agree maybe with a large collapse of material onto the sea surface sometime around 5 o'clock, given the travel time you would need to get to this location. Finally, it's also worth noting that at about between 7:45 and 10:45, there were further instances of lightning and also perturbations to the plume heights. So the eruption, although the largest part of the eruption was really between 4 o'clock and 6 o'clock, the eruption did continue hours later as well at lower intensities. I'm very conscious of time, but very quickly I want to talk about some of the work we're still trying to do to address some of the unanswered questions, which is that, for me at least, the big question is, this eruption on the 15th, it seemingly started in similar fashion to activity which was observed earlier in the episode and in 2009, 2014. So why did we suddenly get a very large escalation in eruptive activity between 10 past and 4:15? So we know from that massive change in caldera bathymetry and the large amount of mass removed that caldera collapse is probably likely, although we're still unsure as to exactly what triggered that. There has been a hypothesis put forward that actually this wasn't caldera collapse, instead that this is an explosion crater blown out. It seems unlikely to me, but it has been put out there as a hypothesis, and so it is possible. Trying to understand maybe what triggered the change in behavior to this caldera-form eruption is some work recently came out by Wu et al., who looked at the water contents of the matrix glass in what was erupted. And what they show is you have a very wide, these are these yellow bars in the top right plot. And that shows that there's a very wide range of water contents in the glass. And so that suggests that actually the magma interacts with water and quench at a range of different depths. And so potentially you've actually got horizontal ingress of water into the magma storage, maybe in the shallow conduits. And so you get reaction over a range of depths. And that also potentially provides a mechanism for boiling large amounts of water, which we know must have happened to get the plume so high. Part of this, so Cornel de Ronde, who's at Geoscience, he led a research cruise to Hunga about this time last year. Among various activities, they dredged some samples. And so Shane Royker is also at GNS. He's doing some work to examine the textures of these samples and see if we can actually piece together the history of the magma ascent, the magma fragmentation, the quenching, and the cooling. And maybe we can use some of these properties, the textures and the geochemistries, to actually constrain the timescales and processes of that magma-water interaction to get some independent estimates of how much water you get into was involved, and compare that to like how much water do you need to get plumes to go so high to generate the amount of lightning. So, to summarize, the eruption was remarkable in many different ways. Specifically regarding the umbrella cloud, we see the spreading transition through different physical regimes with different scaling relationships, and that the spreading front contained considerable vorticity. We also think there was a very rapid transition at around 5 o'clock when supply to the umbrella cloud was effectively turned off, which is about the same time we think there was this collapse. The lightning, the spatial temporal distribution of the lightning in the umbrella cloud was controlled by the vorticity inside it, to the extent that we can actually track the vortex ring at the front of the umbrella cloud and subsequent gravity waves which propagated through the cloud. And the rapid rise and collapse of the plume material also seemingly generated both the Lamb and Precarious waves. And they in turn generated the audible waves, which people heard in the far field. Whereas this collapse probably also generated both local and regional tsunami and fast underwater pyroclastic density caps. Thank you very much.
We can go back to.
Okay, thank you so much. Laura,
Yes. What?
there's some question there. Some question there.
Silvia,
Yes,
can you come closer to the mic?
Actually, it's not a proper question.
The microphones are here. You can speak. No, it is mic.
Okay. I will thank you so much for your presentation. I have some doubts about the increase of lightning in the umbrella. The increase of lightning are connected to the seawater at the source. So the presence of the seawater in this kind of eruption had increased the number of lightning.
Yeah.
Is this okay? So because you didn't expect this kind of number of lightning if the source was not inside the sea.
Yeah.
Okay. Okay. This was my doubt.
Okay.
And the second question is that the number of lightning that you add inside the umbrella helped you in the definition of the umbrella, or I don't know how to say in English. Il numero di fulmini mi ha permesso di fare una stima, diciamo, di tutto il plume oppure solo da parte dell'umbrella? Questo volevo capire.
I think, yeah, I think she's asking if with lightnings you see the whole of the plume or the umbrella region.
Or only the umbrella region?
As in, so it's a really good question.
I also have a similar question. I know
Okay.
nothing about which is
Yeah.
like, about lightnings,
Yeah.
but you locate the lightning
Mhm.
on the horizontal
Yeah,
plane.
we have.
Is there a way?
So there is no depth control.
Okay.
So there's no altitude control. So you have to make assumptions about where it is. So obviously the umbrella clouds, because some people say it's one big fat umbrella cloud, some people say it's two. And also the volcanic plume, which obviously is the whole depth of the atmosphere from sea level to peak of the cloud. Lightning could be happening at any of those altitudes. So we have to make some assumptions. So we have so I think with the lightning that we see in that ring at the front of the umbrella cloud, we have confidence that is in the umbrella cloud away. What the lightning you see in that little dot immediately above the vents, we can't say for sure what altitude that's happening at, but I think it's probably happening in the column above 10 kilometers approximately, because that's the altitude at which you start to form the ice, and that's what you need to generate lots of particles to get the lightning. How high that goes, we're not sure. It may not go as high as the 58 kilometers we see. There's probably not as many particles up there, but is that
Because at that point, the temperature of the atmosphere is higher, I suppose, since it is in the stratosphere, 60
yes, I guess it
kilometers.
is.
So you should count also.
That's a good point. I haven't thought of that.
I suppose that
Yeah.
the temperature is higher.
I guess I don't know whether there would be thermal equilibrium between the plume and the atmosphere. I don't know. But that's a really good point. I haven't thought about that. Yeah.
So
Yeah.
it's
Cool.
only, thank you, for
Yeah. Thank you.
Super.
Any other from here? Yeah, don't know other from here, so I don't know if there's anyone from online.
More question?
If there's nobody online,
There is another one. Come here. And there is another one by Francesco.
So Paul, thank you. And at the beginning of your slides, there was this slide where you identified the zone where the basically plume is buoyant, right? When the density of air become larger than the density of the material. And I was wondering whether these two levels or this area depends, well, I guess the air density is fixed and the density of the material erupted, does it depend also on the velocity or other properties? So you can have differences in this region and how this would affect the eruption, what happened like with smaller or larger?
Yep, yeah, so you're quite right. That curve essentially shows the density of the volcanic plume as a function of height, and that is ultimately controlled by, if you keep the atmospheric density profile fixed, then that is entirely controlled by the conditions at the vent. So that's the exit velocity of the material, the temperature it's coming out at, the radius of that vent. And so, for example, if you had a very wide radius vent, potentially, and it's coming out maybe not super hot, maybe you reduce the efficiency at which you actually entrain air into that mixture, because that's the key to making the plume buoyant. You have to entrain the atmospheric air in, that gets heated up, it expands, it becomes buoyant. But if you're not very efficient at entraining in, then it may never become buoyant, because that's when you get complete collapse and you just get a pyroclastic density currents, essentially. So for the largest eruptions on Earth, that tends to be what happens most of the time. Most of the material collapses back down. You don't get a huge amount of temperature. This eruption is a little bit different, where the diagram I showed is probably too simplistic, where because you've got this eruption which is almost exactly at the sea surface, as well as your hot mixture being tephra and volcanic acids, you're probably also bringing in a lot of evaporated seawater right at the source. And so you're already providing lots of heat, lots of water vapor, which is less dense than the surrounding atmosphere. So in this case, it's very possible that at sea level, your mixture was already buoyant.
Because of the seawater,
because of
the water steam.
Because of the steam. Which is quite unusual, and that probably is that's probably a big contributing factor to why this plume was able to go so high. And so it's been shown with some what we call 1D models, so a very big simplification of the volcanic plume, that you can get the plume going to the 58 kilometers if you basically say that 90% of the mass of the source is steam rather than volcanic material.
No more from here.
Okay, I think that I can stop the record, the registration. And wish to thank Paul for the presentation. And I don't know, Laura, if you want to say something more.
No, nothing except once again, please go on the